Good morning. Welcome to episode number 44 of the ZoomTown Experiment. For today's episode, this will be another one of those update overview type videos. I'm not going to go into heavy code, but I need to set the stage for the next few videos. So what we're going to do today, I'm going to provide a quick update on current development, mostly around the Zcheduler system. I will be showing you how I went about assembling and creating or making the Zcheduler computer. Primarily that'll just be a quick video about the hardware assembly of it. And we'll talk a little bit about the Python dependencies. We touched on that briefly last week. We'll cover it again this week. Then we're going to take a look at an overview of path to travel. That's a very difficult concept that seems to be creating some confusion. And there's been a lot of discussion on it, both online and offline, and we're going to talk a little bit more about that, and that'll set the stage for our next two videos. But in this overview of path to travel, we're going to touch on the shortest path algorithm and the origins of the Zcheduler software, and that one is the Dijkstra algorithm. Then we'll talk again about manual path creation, and then I'm probably going to switch back to the shortest path algorithm, but that'll be the subject of future videos. And then finally, the next few videos will be focused on trip plans and trip plan generation. It might seem like that's a rather trivial case. It's far from trivial. There's a lot to that, and I want to have you understand what goes into getting a Zoomie from destination 32 to destination number 27. Because that's really the core of all my development time right now. And that development and coding is outside of which path choice or path generation software I'm using. Because all that's dealing with is primarily the roads, but there's a whole lot of other things going on along that journey. Now, when we get into the Zcheduler computer system, which I'll be showing a video of that here real quickly, it's made of an Raspberry Pi 4 with an SSD drive on it, heatsink, and a fan, a rather large heatsink. I believe this was repurposed from a file server that I had running on it, and I thought it be better utilized here for the ZoomTown experiment. And especially at the time, if you remember, there was this massive shortage of all kinds of Raspberry Pis not too long ago. But I wanted a custom enclosure for it, so I designed that, 3D printed it. On it are three buttons that we need for helping to control the system. There's a green push button. It's a momentary switch that serves as cycle start or a start key. There is a silver 6-position rotary switch. That was originally intended as a speed override. Frankly, I don't even think I need that functionality anymore. The Zoomie just isn't going that fast, at least not with the motors and gearing that we're using right now. So even at its fastest speed, I can kind of stay ahead of it. And then finally, there's another button. It's red. It's here in the U.S. we refer to them as emergency stop buttons, and those are on almost every industrial machine system out there, and their purpose is to stop everything. Now, in my case, it's a button and it's a latching switch, and it's because all the Zoomies are technically wireless, it's just sending out a code to all of those to actually stop. Here you can see the enclosure. I picked out a yellow color. Looks more industrial, like it should belong in a factory somewhere. You can see all the venting on it, and a little bit of decoration. The Raspberry Pi 4 having the very large heat sink and a small fan on it to help keep it cool. Pi 4s do run a little bit warm, and I suspect with the Pygame software it's going to run rather hot. And we're going to start assembly. I got to go through, get all the switches wired up, so I start out checking which terminals are which so I know the correct ones, solder on some leads to those. It takes a little bit of time. The rotary switch, you got to kind of dig around on that one and figure out which terminals are 1 through 6, etc. So we get those all soldered on. Then comes the tedious process of going through and crimping on the DuPont connectors. I like working with the DuPont connectors. Yeah, they're a bit of a pain. I didn't have any pre-made wires when I filmed this, so I ended up just using regular conductors and then crimping on the ends and then putting on the housings for each of the little pins and so forth. But all told, I think there were 6, 8, 10, maybe 15 wires that needed ends crimped on them and the housings put over them. Always got to go through and update your schematics as you're building things. Helping with wire colors and all that makes diagnostics easy. Assembly started with getting the switches in there with the wires passing through each of the holes. That's a rather simple process. The Raspberry Pi will mount vertically with the USB ports pointing out the top. And now I'm getting that fitted in there, attaching that in place. I'm going to have to drill and tap some holes to mount the base on. Get the knobs all on there and put on some rubber anti-slip feet, and that wraps up construction. So construction itself, rather not too interesting or whatever, but people often like to see those little quick videos. So with that, now we'll move over onto the scheduler computer and start covering some of the more current issues that we're running into. Over here at the scheduler, we're going to take a look at some code segments of both older versions of the scheduler software and a newer version, the one that I'm currently working on. But before we dive into the source code, I just want to give you a quick update on what is going on. You may have noticed I missed a week of video last week or the week before, and I will be missing weeks for a while here, on and off. I'll try to get one out every week, but we'll have to skip some weeks. The testing of this phase is incredibly slow and tedious, and I have to thoroughly vet out all bugs that I'm finding. So that's where literally 90% of my time is being spent right now, is on this debugging process. And just to give you a quick look at what's involved on it, I'm not going to go through and show you all the debugging, but here's what it is. This is my notes, my notepad, so to speak. Here I'm saying problems that need actions. Today's date, I was working on this in the wee hours, 3 o'clock in the morning. I was down here doing test runs. And this flag here, this is this item. It's showing the beginning and ending destination and the roads that I programmed it to take. This first line is the error, the problem that was experienced. In this case, when turning onto road 19, the position is such that it is not seeing the road start magnet. Every road has a magnet at the beginning to help act as a flag. I'm on a new road, and if the approaching turn isn't good enough and it kind of has to swing too wide or something like that, it's hard for the Zoomy's little sensor to pick that magnet up. And that's what I saw in this particular case. And the outcome of that is it caused the Zoomy to turn short of the driveway where it was pulling into, and therefore it either missed the driveway completely or came in at an angle or something like that while it was trying to find a line to follow. And then finally, I have my last note for that particular problem as a suggestion. And I'm going through on a lot of these different paths and so forth, just running them, observing them, making notes of what I think it is. Now, early on in the debug process, I would do one test, spend a lot of time trying to fix that particular problem, go on to the next test. And what I found I was doing, if I would find a problem, I would fix it, but then create another problem. And I wasn't taking the forest view per se. I was looking at the tree itself, the problem. And if I step back like I am doing now, I might see a pattern that I fix in a more appropriate way as opposed to perhaps an inappropriate way. I'm not fixing the root cause of the problem. So that's a lot of what's going on here, but otherwise the layout is all ready to go. There's just some barriers that I got to put up. In fact, I had a Zoomy drive off the world and fall on the floor earlier this morning, but the layout's pretty well ready, so a lot of the efforts here in the scheduler software, and then as I find behaviors on the Zoomy, I try to clean up the code there here on occasion as well. But frankly, I almost went 3 weeks without needing to update anything on it, so that's telling me it's pretty stable. Now let's get into the discussion dealing with these route planning or trip planning and all of that. And that's where we're going to go back to an earlier version of the software. And this won't make a whole lot of sense, and I don't want to spend a lot of time on this particular one here, but this is the Dijkstra algorithm. It is a shortest path algorithm, and it really makes sense for what we're doing, right? You give it a start and an end point, and then there's a list with all the intersections. Joints, I think, is their phrase for it. And it will automatically go through, sort out the shortest path there. Very powerful routines. There's many varieties of them. Early on when I was doing research for this type of planning, which is probably going back about 10 years, which was the last time I used it, I was working on a larger robot that needed to navigate through an office environment. And the only purpose was to have, say, go to this location, and it would follow along and get to that location. And I never really explored deeper into it, and I wish I had. Now, luckily, Tomek gave me a heck of a great education on this routine over this past week via emails and so forth. And I'll go into more details about that in next week's video, because that's where we're going to do a deeper dive in all of this. But anyhow, in this older version of the scheduler software, all this planning on how to get from one location to another was planned to be done by a routine that automatically generates that path. Now that path is literally only the roads, such as the driveway. You're going to get to the road, take this road to this road to this road, pull into a driveway. It doesn't deal with all the little details, such as, do I stop at this intersection or just drive through it? Do I have to make a sweeping turn or a pivot turn? Is the pivot turn crossing a traffic lane needing to stop so you don't hit the oncoming cars? Or do you just drive through because it's a right turn and there's no way to hit anybody? So there's a whole lot more to this whole process. But it did start out using the Dijkstra algorithm to provide the basic route plan. Now, if we come forward where I'm at right now, I've been mentioning that I abandoned the Dijkstra routine because I was fearing how everything would just end up going through the center of the town. All 16 zoomies are trying to get through this funnel at the center of one end to the other of ZoomTown. And that's what we'll cover next week. But let's get back over to here. This is our current scheduler software, and as I mentioned, let me get it running here so it makes a little more sense. Last week I had mentioned there's two modes to it, a programmer mode, and that allows me to manually create a trip plan, a set of instructions to get from one location to the other. And that allows me to create a trip plan, a set of instructions to get from one destination to another destination, and then we communicate that over to the Zoomie for it to follow that course of action. More importantly, this whole software started out just as the system to run the experiment, telling each Zoomie randomly to go here and go there at random times. And of course it did evolve into where we are now with two modes on it. Now, again, I want you to understand what's going on here so that everything makes sense, more so in the next video and the video after that. We think of a trip, and I'll kind of program one here. Let's say I'm in destination 31. Over here on the layout, the Zoomie would actually be right there. And I'm in destination 31. And let's say I want to get over to destination 14. So to do that, I have a lot of different options. In this case, I'm going to go up this road, over to this road, down this road. Remember, here in the United States, we drive on the right side of the road, not the left side of the road. So we'll get over to here, and then I'm going to pull into destination 14. I process it, I simulate it, and it just shows a very primitive point-by-point motion of the Zoomie taking that trip. And then finally select the Zoomie and run. Now, as you can imagine, going around this path, like backing out of the driveway, well, you can't just back out of the driveway, right? That's all I've told it here was to go from the driveway to the road. Well, in order to go from the driveway to that road, first I got to check to make sure there's no traffic coming. That information would come from the scheduler. If the scheduler says there's no traffic on that road, you're free to back up. Okay, now I need to back up. Well, that coming in and out of the driveway is a little bit trickier because we need to use more than just the encoders for figuring out how far to back up. So I have to use different sensors to perform that particular motion. When I'm backing up, I can't use line following. That won't work at all. So I'm using the encoders for position, and I'm using my forward-looking crash detector, the cone of light sensor, to also help guide me on how far to back up. Because I need to back up so that when I make a turn to line up with the next road, I'm in the right location to make that turn. So to get out of the driveway, here are the steps. I would first ask permission from the scheduler. Am I okay to move? It checks the traffic. It says, okay, Zoomie number 1, you can move. So then I back out of the driveway to line up for a turn. Now, because I'm backing out of a driveway, every driveway will exit a road and enter a road. It will never enter a road at its start. It will always enter a road somewhere in the middle of its length. So I need to know which direction that road is because I got to turn either left or right so that I'm pointing in the right heading. Back to this example, if we're going to back out of the driveway to about here, let's see, about here is my guess. So I'm backing up to this location. Then I'm going to say I need to go north. Up is north on the layout here in the actual physical layout and here on screen. So road 21 is going north. In order to go that way, as I'm backing up, I need to turn the wheel to the left. So that would be a left turn. I turn the wheel to the left and make a pivot turn. It's not a sweeping turn, it is a pivot turn. A pivot turn steers with one wheel stationary and the other wheel, the outboard wheel per se, would rotate, in our case, backwards the right amount so that it makes a 90-degree pivot. And that gets me lined up to make the next move. And then I would go into the next phase of this. I'm entering this road in its middle somewhere. Remember, I just mentioned that every driveway I pull out of, I am going to back into the middle of a road somewhere, not at its start point. That's where this starts getting really involved and really tricky. Every time I transition from one motion to another motion, or one destination to a road, or from one road to another road, there's a whole different set of rules that have to be played out. So let's take a look at what happens when I get onto road 21. Okay, so I backed out and I'm sitting here and right here on the physical layout. Now, we think we know where we are on that road, but we could easily be off by a ½ inch or more. I'm backing up using encoder steering, which isn't super accurate. So I could be wandered a little bit south or wandered a little bit north. So we don't want to assume where we are. And that was the purpose of putting in magnets. On the real layout, hopefully the camera can see this. Maybe not from over there. This would be where the magnet location is. And I'll get the zoomy back. And on the layout here, or on the scheduler, that little light gray circle is that magnet. So I back up, I'm pointing in the up direction or north direction, and that is the first magnet that the zoomy will encounter when it starts moving forward. So I have to give it, to allow for more accurate localization, in that command, to move forward, say, the next magnet you see, you are going to be at position X such and such and Y such and such. So when it gets to this point, the internal tracking of where the zoomy is gets updated to that absolute position, which is relative to the origin point of the whole layout there, and of course here on the screen. And that origin point is up above in the left-hand corner in the upper left corner, with X plus going right and Y plus going down, which is opposite of graphing but normal in computer graphics. So now I'm localized to that line. From there, I'm going to go to some distance along that line. In this case, we would go, say, all the way to the end of the road. Well, this next section here is a sweeping turn. It's not a pivot turn. So there's a different set of maneuvers to go through that. You'll also notice at that location, we're up here. Get the mouse up there. We're right in this area. And all I need to do is get to this point and then make that, follow the line, the guideline on the layout around the corner. No need to stop. There's nothing I can run into, no cross traffic, etc. When I get to that point of the start of the next line, again, a different set of rules. We're starting at the beginning of that line where there will be a magnet 1 inch in from the end of the road, and that's on the opposite side, the left side of the zoomy. So when the left Hall effect sensor sees that marker on the left side, it says, okay, I just found a new road and I'm at the position of 1 inch along its travel or along its path. I can update the absolute position at that location. And this happens in a wide variety of scenarios all through its travels. It's extremely complicated. There's a lot going on because we're not just going road to road. There's more going on in between, and the rules are very subtle, which is, I could have laid this out a whole lot easier to make the rules very simple for driving, but what's the fun in something if you don't suffer a lot in the debugging process? Now, I just want to show you a real top-level view of the code, and I think with that, we've got a foundation for what we can use to our next few discussions. We'll close this out, and I'm going to scroll down here into the middle. Now, first, I just want to show you how the data is organized, and this is a very brief overview of it. Okay, this is all the coordinates for where the destinations are, the roads, the magnet locations. All this data is stored in separate lists. In this case, destination coordinates, all those contain is an X and a Y location. So that's pretty straightforward there. The list for all the roads, the actual roads, are listed in a data list called ZT. That tells me which direction the road is, its heading, its start point, its end point, and the color is black. And that's just a flag for when I plot the road on the screen. And then the distance from the start of the line to the end of the line. And that's what these are. Over here, I've just got notation of which road's which. At times, you'll see arrows drawn on the guidelines so that I could keep track of, yes, we drive on the right side of the road, and it would be easy to keep track of which way we're going, but I got confused early on, so I just added a little more graphic detail there to show which way that road's actually allows you to drive. Then when we're selecting roads, we've got this function here, or this list called selected roads. Each time I select one on a path, that gets logged into this list. And it's a fixed length list simply because there's only X number of roads you need to take to get from any point to any point. For simplicity, I limited it to, I don't know if it's 25 lines or something like that. But this data pretty well matches the same as the road data from this list up here. And then finally, all the magnets. And I call them inch magnets because it started out they were every inch in relationship to each other, and they're representing an inch location. But every magnet, its position is listed in this list. And I've got the notation here, which road has which magnets and so forth. So from all that data, I have to look at our scenario, where we are, find information from each one of these lists, and then make the right decisions and calculations for the Zoomy to move. So that's the data format. And that's been pretty consistent from the old software using the Dijkstra algorithm up to the current way. Now let me zoom up. As each road is being executed, that was selected when I created the plan, or that Dijkstra would create in its list of destinations and roads, I would go through each part of that list line by line, which would be essentially road by road, and I would look at that data, determine what type of interaction this current move is and in relationship to the next move. And that's what this function here is doing. Drive road 2, meaning it's going to drive a road. And the 2, in this particular case, means this was version 2 of it. But we look at all the data, and from this I can figure out what type of motion I need to make along the way of this road and what to do at the end of it. And from that, I will make a decision which type of operation I will perform, or which type of combined motion events I need to perform. And you can see that I've got these things here. If current move is a road and the previous move was a driveway, the only time that occurs is when I back out of a driveway and I'm on a road. Likewise, if I'm going from one road to another road, which is a lot of the trips, but there's many combinations of that, I can exit at the end of the current road and start in the middle of the next road. Or I can exit in the middle of the current road and start at the beginning of the next road. Or I've got two roads that go one road straight into another. So inline roads end to end. I can also go to the end of the current road and then start on a new road. All of these require vastly different behaviors and motions in between each of those roads. And then finally, the last one would be if I'm on a road and my next move is I need to pull into a driveway. So that's how I parse through the list of our roads. And then we go through each of these bigger functions. And I know it's probably small. It's about as big as I can make it on the screen and still get most lines in here, but just let me get to the top, which should be this one. Okay, BOD 2, back out of driveway version number 2. What that has to do is take all the data from what's in those lists that we've compiled together, based on the heading of the road and the heading, or based on the current heading of the road. It has to make a decision on how to back out, which way to turn, and all of that. And that's what all this data is. And from here, we'll set up our backup headings and then our road headings. And finally, these are the instructions. I say add instructions. There's 4 of them for this to get out of the driveway. Because this is the very first motion, I know this is the beginning of a trip plan. So I write that instruction out. There's no other time other than backing out of a driveway where it's the true beginning of any trip. We need to stop before I back out of the driveway. Remember, I says I got to ask for permission whether I can move or not. Then I perform the backing up maneuver. That's abbreviated with BOD, back out of driveway. I update our global positions as I'm doing these movements so that when we do the simulation, you see how the icon for the zoomie moves around the map? That's the position it's using. I also pass that information into the zoomie so that it can also update its coordinate systems. And then finally, when we back up, the last instruction it has to perform is to do a pivot turn and get into the correct heading that it needs to go. So backing out of the driveway requires 4 very specific steps to be performed. And every single one of these motions has a different set of those motions that have to be performed. Now, road to sweep turn. That is like I've got over here. Hopefully you can see I'm moving my hand up there. I'm on a road and then I'm going to go into a sweeping turn. Well, that's this behavior. Again, take all the data, make decisions based on headings, etc., and then create the final moves. In this case, FLS, meaning follow line straight, and that will take it along the road. And then when you get to the end point of that road, we will then do an FLM. And I actually forgot what the M stood for, but follow line motion, I think, is what it was. And you'll notice there's no inch markings or anything like that on this area. All I know is I've got to follow that a certain distance, and that would be 2 pi r times 0.25, a quarter of an r, or a quarter of a circle. So it's pretty easy to calculate it out. And that finishes that move. And that's how this whole thing works out. Now, every little area on the layout has somewhat special little situations that create problems. And that is part of what the testing process is right now. I can't go any further with anything until I get this thoroughly vetted out. Once it's all vetted out and things are working very robustly, very reliably, then I can put in the final refinements of how everybody interacts, and then we can start with experimentation and so forth. So with that, I'll wrap up this video, and I just want to talk quickly about what we're going to do in the next 2 videos, because a lot of what I said today is going to apply to those 2 videos, and you'll get a much deeper understanding of how this whole thing works with regard to these trip plans and driving instructions. But in the next episode, what we're going to start with will be from the scheduler's point of view. We will go through and explain each of the motion commands and what they mean. That would be FLS, BOD, FLM, and all that sort of thing, and then what their parameters mean. Then we'll program a trip and go through and look at all those motion commands that it creates, and ultimately we'll send over to the Zoomie. The following episode, we'll look at it from the Zoomie's perspective and what it is doing with that data and how it executes the trip plan. In between these episodes, I want to try to do this every week, but I just know in the reality of it, how complex and how slow this debugging process is, I'll probably have to skip some weeks between then and now. It's just, unfortunately, I can only do so much with the time I have for this. But I think with all that, we're at a good point right now. We'll wrap up this video, and I will look forward to seeing you in the next episode. Thanks again for watching.